Yeah, welcome to this lecture. We're going to talk about generating subset through stack manipulation. So, what is the motivation? Describing generation algorithms, is an important element in data structures and algorithm domain. So, what this means is, so what this means is that there are problems like gaming. You write programs for gaming and search. So, for example, as a simple problem, suppose you are gaming, then you would have to generate your the next moves given the current move. Not only the next moves, the moves of your move and the opponent's move, and then your move again. So, what it means is that given a particular move, you need the ability to generate the future 3 or 4 moves. So that is the generation algorithm I'm talking about. Similarly, when you're searching, let's say for example, you're trying to find if there is a path between A to B, then you need to generate all possible paths from A to B to check out which is the shortest path. It's just an example. There are various algorithms of shortest path, but I'm just giving you the need for generation, the ability to generate. Is very, very fundamental to gaming and search kind of problems. They typically involve recursion, and recursion puts off many starters. So what I thought was recursion is nothing but some kind of stacking approach. So what I thought was, let's remove recursion and let's write a program to show how the same can be achieved through stack. This is a standard computer science principle where recursion is replaced by completely by manipulating stack. Right? Recursion is nothing but stacking. But what we are trying to avoid here is that there is no recursive code at all. It's completely based on stack manipulation. You definitely need to know the basics of Python to understand this code, because the code itself is Python. All you need to know is about set operations and a for loop. So let me move on now further. So what's the generation idea? So let's consider the set 1, 2, 3. So how do I go about generating? So for generating subset of 1, 2, 3, I will say, hey, the subset contains 0 elements, 1 elements, 2 elements, 3 elements, and 4 elements. So let me first generate all the subset with 0 elements, and that would be the null set, right? Now, so that is done. Now let me generate all the subset with 1 elements. Now, given the subset is 1, 2, 3, 4, one way to generate, subset with 1 elements is take the null set and keep on adding all the elements that are present in the current set. If you add 1, the subset 1 is made. If you add 2 to null subset, the subset 2 is made. Similarly, subset 3 and subset 4 are made. So the important point to observe here is that given this previous subset, I am able to generate the current subset. Given the subset with 0 elements, I am able to generate subset with one element. Right? So that's what this is telling you. If you go to the next slide. So generate all the subset containing 1 elements. That's how I generate. I add 1, 2, 3, 4, or I append 1, 2, 3, 4 to the null subset. So if I append 1 to the null subset, I get the subset 1, set 1. If I append the element 2 to null subset, I get the subset 2. So again, re-emphasizing, by adding, we are generating subset containing 1 elements based on 0 elements. So that is the fundamental principle I'm trying to build it here. Next is how do you generate subset containing 2 elements? Just give me a minute. I'll just erase all the inputs in the slide. Okay. How do you generate subset containing 2 elements? Use the same principle. If you have subset 1 element, then what you can do is that you can add all the elements which are greater than 1 into this subset and generate the subset containing 2 elements. So suppose I take the subset 1. To it, if I add 2, I'll get the subset 1, 2. If I add 3, I get 1, 3. If I add 4, I get 1, 4. Right? So again, going back to the principle, I am using subset containing 1 element, and I am generating all the subset containing 2 elements. Right? The same can be done for 2. Similarly, 2 would generate the subset 2, 3 and 2, 4. right? So what I'm demonstrating here is that you can generate a subset containing k elements based on subset containing k minus 1 element. So that is the generation algorithm here. So that's what this is showing next. That 1 will generate 1, 2, 2 will generate 2, 3, 3 will generate 3, 4. Now generate all subset containing 3 elements. So what would you choose? You would choose first 1, 2. Now 1, 2 would generate the subset 1, 2, 3 and 1, 2, 4. Right? That's what it will show you, right? 1, 2 will generate 1, 2, 3, 1, 2, 4. 2, 3 will generate subset 2, 3, 4. And similarly, subset containing 4 elements will be generated based on subset containing 3 elements. So, and hence we take 1, 2, 3 and generate the subset 1, 2, 3, 4 by adding 4 to it. So, if we take the subset 1, 2, 3 and add 4 to it, it becomes a subset 1, 2, 3, 4. Right? So, this is the fundamental principle. Now, if you take the subset 1, 2, 4, there is no element greater than 4 that is present in the original set. So you cannot generate any subset out of it. So there is no subset possible from element 1, 2, 4. So again look at the set containing 1, 2, 3, 4 and let's look at the tree which we said. So here one can imagine that the subset containing 0 elements is the parent of the subset containing 1 elements. The subset containing 2 elements, or the arrow anyway, which way you want the arrow to be. The subset containing 1 element is a parent of subset containing 2 elements because subset containing 1 element is used to generate subset containing 2 elements. And similarly, subset containing 2 elements is used to generate subset containing 3 elements, hence it becomes its parent. So this is the parent-child representation which you are going to see now. So here it is. When I have a null set and I add 1, 2, 3, 4, the candidate when there is null set, the candidate elements that can be added to this subset to create a new subset. Sorry, let me repeat it again. So when you have null set, I can add 1 to it and generate 1, 2, 3, 4. So I added 1 here. If I add 2 to null set, it becomes subset 2. If I add 3, it becomes subset 3. If I add 4, it becomes subset 4. Now I use subset 1 and generate elements subset containing 2 elements. How would I do that? If I add 2 to now this subset, it becomes 1, 2, is generated. If I add 4, 1, 4 is generated. Now if you take for example 1, 3, that's before the diagram, let's see what can be added. Now 3 is the largest element. The only possible element you can add to this set to generate a subset is 4. So 3 will generate 1, 3, 4. Let's take a look at that. Now 3 will generate 1, 3, 4. Right? Now another thing to observe here is that the way I am printing the subset is that it's in a breadth first search, which means that all the siblings are printed. So first all the subset containing 1 are generated, not even printed, they are generated. All the subset containing 1 elements are generated. Then all the subset containing 2 elements are generated. All of them, right? All of them are generated. Then the subset containing 3 elements are generated. And finally the subset containing 4 elements are generated. So this is called the breadth first search because you're the breadth first walk, because you're generating the subset, all the siblings first, then the next sibling, so on and so forth. So this is good. So this visual representation helps you to understand the generation problem. It's a good thing to draw and keep things clear. Now let's take a look at the Python. So what's there in the Python code, right? So the Python code is fairly simple. So initially the subset is null, and the last element is 0. So let's take a look at it. The algorithm is very simple. When the subset is initially null, what do? I iterate from last element plus 1. So last element is initially 0. So last element plus 1 will be 1. Right? And set of minus 1 plus 1. Set of minus 1 is the last element of the set, which is 4. 4 plus 1 is 5. So I iterate from 1 to 5. Iterate from 1 to 5 means the element will take the value for in each iteration it will take the value like 1, 2, 3, 4. In the first iteration it will take 1, the fourth iteration, last iteration it will take the value of 4. And what I am doing, and every time I am inserting, can you take a look at it? I am appending the element, I am appending this to the new subset. So initially new subset is what? Initially, okay, let's come to that. So new subset is a copy of subset. So what is subset initially? It is null. So new subset creates a copy, it also becomes null. And to it, iteratively what I am adding, new subset is null. Then what I am doing, new subset append add element. Element in the first iteration is 1. To the null subset, if I add 1, it becomes 1. Then what I do an important thing, I insert it. You can take a look at it. I put it in stack. So if you put it in stack, what is going to happen is this 1 is going to go inside the stack. Then I am similarly inserting 2 in the next, that goes inside the stack. Then 3, then 4. So that's the first iteration. So after the iteration is over, at this point I say subset is subset stack of pop 0. Pop 0 means take the 0th element. So 0th element now becomes this subset, right? So subset now becomes the set 1. Now again I go back to the iteration. I do last, what is last element here? Last element is a subset of -1. So subset of -1 takes the value of 1, right? Now I go back. So at the end of first iteration, last element would have a value of 1. Subset would have the value of set list 1. Just continue this. So let's go back to the iteration. It goes back to the iteration. Now in the second iteration, last element will become 2 and set of -1 remains 5. So what is subset? Subset is still 1, right? So essentially I have generated 1, 2, 3 and 4. I don't have space, so I'm not able to write it. Now, as I said before, subset now points to 1. Again I iterate. Now to the subset 1 I add element 2, because now element ranges from 2 to 5 and hence it becomes 1, 2. So at the meanwhile, what is there in the stack? If you take in the stack, the element 2 is present, element 3 is present, element 4 is present, and I generate 1, 2 and I add further into the stack. So it becomes 1, 2 is present. Next the element 1, 3 will be present and 1, 4 will be added. At the end of iteration, I pop 2 and then generate all its children and then add it to the stack. So this process continues. Okay. Now I have drawn this also. So this I have given an explanation. So let's try. So let's see in action in diagrammatic. So initially it's a null set. So when it is null set, last element value is initially 0. And so last element is 0, so last element plus 1 will become 1. Set of -1 plus 1 will become 5. So the iteration is from 1 to 5, excluding 5. So all 1 to 5 you are adding to the element null. So which means it will generate the first iteration. Subset.append will push 1 into the stack. The second iteration it will push 2 to the stack. The third iteration it will put 3. And the fourth iteration it will push 4. After this iteration is over, what do? I say subset equals subset pop of 0. So subset, currently the set is here, so pop of 0 will return the element 1. You print 1 and then what do? This iteration generates, this particular loop generates all the children of subset. This loop actually generates all children of a subset. So this all children of 1 containing 2 elements is 1, 2, 1, 3, 1, 4. So all children of 1 are generated and they are pushed into the stack. Next, when this iteration is over, what do? Use subset equals subset pop of 0, which means what does subset become? 2. This iteration now will generate all the children of 2. 2, 2, 4, 2, 5. 2, 3, 2, 4. Next 3 comes. Again, this loop goes on. The loop generates the children of subset. All the children of subset containing one element extra. So if it is 3, it generates 3, 4, 3, 5, 3, 4. 4 does not have any child because that's the last element. Now 1, 2. Let's see how 1, 2 works. Let me clear off this. So now the subset is 1, 2. Now if the subset is 1, 2. So it prints 1, 2. What is the last element of subset? Subset of minus 1. So last element is subset of minus 1. Subset of minus 1 is 2. So in this iteration, last element takes the value of 2. And here it comes back again. And because it's in a full, remember it's in a while loop, non-ending while loop. So last element becomes 3. And set of minus 1 becomes 5. So you have 1, 2 as the child. And what you will do, you iterate for, you add 3 to it and generate the set 1, 2, 3 and push it onto the stack. Then you add 4 to it, you generate 1, 2, 4 and push it to the stack. Because the iteration is running for element 3 and element 4. So that's what it's doing. It's adding 1, 2, 3 and it is pushing into the stack. Right, so this continues. You can generalize this. So when does it stop? It stops when it reaches 1, 2, 3, 4. Now when you reach 1, 2, 3, 4, the last element would become what? Subset would be 1, 2, 3, 4. Okay, it will print the subset 1, 2, 3, 4, and last element of subset will be, last element will take the value of 4. Right, last element is 4 here, so it will become 4. It goes back to the iteration. So the iteration element now iterates from 5 to 5, and it's not even possible. So it comes out of it, and then it does subset dot pop 0. So there is nothing in the stack. So it throws an exception, and you come to this point because the stack is empty, and it says all subsets have been printed. Right? So this is the algorithm. This is the fundamental algorithm. Just to repeat, what the code does is, at any point of time, it uses the previous set and generates all its children. It pushes all the children into the stack, and then the process continues. Okay, so that's what happens. So that is the algorithm, and like I said, it prints all the siblings first, then their children. So that is the order in which it's printed. Now that's the conclusion of this. To check whether you understood the problem or not, the next problem that you would try out was to generate permutations. What permutation means is that, suppose I say generate all the permutations of 1, 2, 3. All the permutations of 1, 2, 3 would be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. This is an example of 3. Similarly, 4 will have its own number of permutations. So your thing is, there are two things to this problem. One is you have to draw the tree representing what is a parent and what is a child. How do you generate? So for generation algorithm, you have to first identify what is a parent and what is a child. The second thing is write a program. Obviously, write a program for generating this, right? Generating a subset. An additional program which I can think, which is not unfortunately documented here, is that right now the way subset is printed is, suppose this is the tree, the way subsets are printed is its breadth first, which means all the siblings are printed first. Instead of it, suppose I asked you to change the program such that you print the children first. First you print this, then you print its first children, then its first child, then its child, then its child. Now all the children are now printed. Now you print its second child. So this is called the depth first search. So you print the children first, not the siblings. So can you change the code to for the subset problem to print the children first instead of the siblings? So that's all for this subset assignment. subset generation through stack. Thank you.